The purpose of our project is to solve an everyday problem that we all have encountered at least once. Have you ever had to run a few errands as quickly as possible? After a long day of school or work, having to run errands after can be a bit of a drag. We plan to solve this problem by finding the shortest path between all stops in the least amount of miles, starting and ending at the same location. We will accomplish this by using Dijkstra's algorithm in order to find the best path.
So for our project, we decided to use a shortest path algorithm to solve the problem of running errands after school or work. Although Google allows you to add multiple stops, my biggest drawback with the application is that it does not optimize the route. Since we're all very busy, it would be ideal to be able to make all of your stops in the shortest amount of miles. We could do this by applying Dijkstra's algorithm to find the shortest path in the least amount of miles. To find the shortest path, we make each stop a node and we calculate the distance between each stop, which will give us the weight of each edge.
Dijkstra's algorithm works on any subpath from one vertex to another vertex. We want to evaluate the distance of each vertex from the starting vertex. Then we visit from the starting vertex and its adjacent vertices to find a subpath to those adjacent vertices. Consider a graph with 4 vertices 1, 2, 3 and 4 as shown in the figure below. We choose the starting vertex as 1, then go to each of the adjacent vertices and update its minimum weight. Here there are 2 adjacent vertices, 2 and 4, and their weights are, let's say, 3 and 1 respectively. Now we update weight 1 in the shortest path. If the shortest path of the adjacent vertex is lesser than the total of a new path, we don't update the new path, but we update the shortest path of the adjacent vertex. Now here there are 2 adjacent vertices of vertex 4, and those weights are 5 and 7 respectively, but the new path is greater than the shortest path of the adjacent vertex of the starting vertex, so we ignore it. Now we add the shortest path of adjacent vertex of the starting vertex in the shortest path. We then repeat until all the vertices have been visited. Thus, we get the shortest path.